Here, we have a continuous function f of x. If we had 2 points on this function, f of a and f of b, what would the average rate of change be over that interval? Well, because the function is continuous, no jumps, gaps, or breaks, we know that this would just be the rise over run, or the change in y over the change in x. So that would be f of b minus f of a over b minus a. This is the average rate of change. Now, can you find the instantaneous rate of change at point A? What we're trying to find here is the slope of the line tangent to that point, or the line that touches the function at only point A. In calculus, the slope of the tangent line is called the derivative. So how can we find the derivative of f of x at A, or the slope of the tangent line? In order to find the derivative or the tangent line, the function will have to meet 2 conditions. First, the function must be continuous. Consider this endpoint discontinuity. Can we find the tangent line at this endpoint? Well, no, because there are infinite ways that we could draw tangent lines that touch this point. So the first step to finding the derivative is a continuous function. Now, the function must also be differentiable. This means the function is smooth, not just connected. Consider the absolute value of x. Even though the function is continuous, at 0, there are infinite tangent lines. This is because there's a sharp corner on this graph. A good relationship to know is that if a function is differentiable, it will always be continuous. But just because a function is continuous doesn't mean it's differentiable. Keep this in mind as we're finding derivatives. Now, if we put a point x to the right of a, what is the slope of the secant line of these 2 points? Well, it's just the rise over run. So that would be f of x minus f of a, the change in y, over x minus a, the change in x. Now, how good of an approximation is the secant line to the tangent line? Not that great. But what happens if we move x closer to a? Now it's looking better, but it's still not great. What happens if we move x even closer and the distance between a and x becomes infinitely small? Now the secant line begins to look a lot like the tangent line, and we get a really good estimation. So as point x approaches point A, the slope of the secant line that passes through point x becomes a good approximation of the slope of the tangent line at A. Using our limit knowledge, we know that this is the limit as x approaches a of f of x minus f of a over x minus a. This is the derivative. Using this limit, we can find the slope of the tangent line, or the derivative, at any point of a function. Now, let's consider another way we can define the derivative using limits. Instead of focusing on another point, let's focus on the distance between a and the point. Let's call this distance h. So the x value of this point would be a plus h, and the function value of this point would be f of a plus h. Now, what is the slope of the secant line that passes through both points? It would be f of a plus h minus f of a, the rise, over a plus h minus a, the run. As the distance h gets smaller and smaller and approaches 0, the point on the function, f of a plus h, will move closer and closer to f of a, which means the secant line will become a better match for the tangent line at f of a. This is the limit as h approaches 0 of f of a plus h minus f of a over a plus h minus a. Now, in the denominator, we could choose to cancel out the a's, since a minus a is 0. This leaves us with only h. So this here is another way we can define the derivative using limits. Okay, now let's see derivatives at work. Given the function x squared, what is the derivative of this function at 2? Let's put a point to the right of 2. As this point, x gets closer and closer to 2, the secant line becomes a much better match for the tangent line or the derivative. So let's use our limit definition. As x approaches 2, what is f of x minus f of 2 over x minus 2? Well, we know that the function is x squared. So our numerator would be the same as x squared minus 2 squared, and we know that our function x squared is continuous, so the limit must exist. Now, if we go ahead and directly substitute 2 in for x, we get 0 over 0, which is indeterminate. So let's try some algebraic manipulation. Using our knowledge of perfect squares, we know that x squared minus 4 can be rewritten as x minus 2 times x plus 2. Now, notice that the x minus 2's will cancel out in the numerator and in the denominator. This simplifies to x plus 2. And now, if we directly substitute in the 2, we get 2 plus 2, which is 4. So that's our derivative. As x approaches 2, the limit of x squared minus 2 squared over x minus 2 is 4. Looking at the slope at 2, 4 seems like an appropriate answer. Now, we could also use our other definition here. Our x point is 2, and our function is x squared. So we have 2 plus h squared minus 2 squared in our numerator. Now, what is the limit as h approaches 0 of 2 plus h squared minus 2 squared over h? Again, if we directly substitute in for h, we get 0 over 0, which is indeterminate. So let's try some manipulation. What is 2 plus h squared? It's 4 plus 4h plus h squared. Now, 2 squared is 4 also. 4 minus 4 is 0, so we can get that out of the way. Now we have 4h plus h squared over h. And what can we do here? Well, if we factor out the h in the numerator, now we get h times 4 plus h. Now, the h's in the numerator and in the denominator can cancel out, which leaves us with 4 plus h. Now, if we directly substitute in for 0, we get 4 plus 0, which is 4. And that matched our limit earlier, so it looks like we found the derivative here as well. Awesome work. Unfortunately, there are many ways to notate derivatives. All of these notations mean the same thing. The first two notations are the most commonly used notations, and they'll get you through tests like the AP exam. And there you go. That's an introduction to derivatives. Using our knowledge of limits and continuity, we found a way to determine the instantaneous rate of change of a function, also called the derivative. Now, if this video helped you or you found something useful, hit the like button, subscribe, and share it with a friend. These videos take a bunch of time to make, so subscribing will mean a lot. Also, check out my recommendations in the description. Now, keep working hard and keep learning. Thank you for watching.